module 13.4, we're still talking about the idea of optimizing some given function, but now we're going to be doing that using a different approach called Lagrange multipliers, or Lagrange multipliers. I'm never totally sure if I pronounced that correctly. But in this case, what we're going to be dealing with is problems that we want to optimize some given function subject to some given constraints. So we're going to have some additional information that we need to apply into our problem. So let's talk a little bit about the method, what we're going to do for these problems. Before we even do that though, we want to introduce lambda. Lambda is a Greek letter that's kind of this, I don't know, slanted pole being propped up by a leg. So lambda is just a Greek letter, and typically when we get into math classes we start mixing in letters. Way back when you started algebra, that freaks people out. When we start mixing in more Greek letters, that tends to freak people out even a little bit more. One of the main things to keep in mind is that all this is just a symbol. We could have easily just used the letter L, the letter S, any number of other things, but just out of convention, people use this Greek letter lambda. What's important to keep in mind is that this symbol has absolutely no meaning until we assign one. So some symbols in math kind of have an inherent meaning. The integral symbol has an inherent meaning, but this is just the same thing as using an X, Y, A, B, or C. We're just using this specific symbol that's used so that people kind of look at this and know more intuitively what we're talking about. But for our purposes, this letter lambda is going to be referred to as a Lagrange multiplier. So again, it doesn't have any special properties. We just treat it like we would any other variable in our problem. So it's simply a new variable which we will introduce and then solve for. So we're already dealing with multivariable functions. They're going to be x's and y's as independent variables. We're going to introduce a new variable, and more or less our ultimate goal is going to be to solve for this value for lambda. So our method is going to be to first write our problem in the form maximize, or if what we're doing is a minimization problem, minimize. So typically we're interested in maximizing profit, minimizing cost. So we have some function that we either want to maximize or minimize, subject to some given constraint, g of x, y, and whatever that constraint function is, we're going to set it equal to 0. So then we're going to form the function capital F of x, y, lambda. So we're going to use these two functions that we have, we're going to combine them to create a new function, which will be f of x, y. So this is the original function that we want to optimize, either maximize or minimize, plus lambda times whatever this constraint function is. So once we know these two functions, setting this up is as simple as just multiplying that second function by lambda and adding those two results together. Then we want to find the critical points of f, which means we're going to end up needing to solve a system of equations, which is this function capital F differentiated with respect to x, setting that equal to 0. We'll take capital F differentiated with respect to y, set that equal to 0, and then we'll take capital F and differentiate with respect to lambda, this new third variable that we're introducing, and set that equal to 0. So there's a little bit more work in some senses in this case. We have to create this new equation. We have to deal with this new third variable. One of the perks of this approach, though, versus what we introduced in the last module, is that we don't need any second derivatives. This is all just based off the first derivative of this function. So after we solve that system of equations, if we end up with one critical point, x naught y naught, lambda naught, so whatever those three values are. Then we assume that x naught, y naught, or x sub 0, y sub 0, is our solution. So if we only end up with one critical point, we assume that's our solution. Lambda gets dropped from the solution and it's just in terms of x and y. If we end up with multiple critical points, then we evaluate the original function at each value. So we take each of those critical values that we came up with, the corresponding x and y coordinates, plug them into the original equation. The largest of those is the maximum, and the smallest of those is the minimum. And that's our method. So essentially it comes down to constructing this equation, finding those derivatives, setting them equal to 0, and then solving that system. The easy case is when we come up with a single solution. If we come up with multiple solutions, then we have a little bit more work ahead of us, but just some basic arithmetic and then comparing those results.